Okay, let me quickly give you the idea of this project. So basically, Julia is a new programming language. Like its main purpose of this programming language is for a statistical, I mean, not statistical, scientific computing. I mean, all kinds of scientific computing can be, they want to develop a statistical language, sorry, a computer programming language, which can do the computing very easily. It should have the, advantage feature of like easily programmable, high level kind of programming. So if you have a, so sort of almost like a pseudo code with some little bit of syntaxing, it should be able to apply it. It should be able to run kind of thing, and it should have, it should able to process as fast as C or Perl, and it should be able to um, do the things, handle big data. So these are the main features that Julia claims to achieve. Some of Many things they have already achieved, many things they need to achieve further. Now, what they have done, it's about 10 years old, and one of the founder, there are four founders. The main idea was by Alan Edelman, and he's a professor of applied mathematics at MIT. And so their idea, and another founder is Viral Shah. Interestingly, Viral is close, uh, connected to my colleague Ajay Shah and Susan Thomas, and that's how we got the project to run. Now, this idea of uh, that it will run as faster than R or Python is coming from the idea that R or Python is a interpretable language. It means every language, every step you write in Python or R will go to C++ compiler or a Fortran compiler, and then it will compile and compute, and then it will come back to the R or Python. So there will be a communicating, always there is a communicating between, back and forth between R, Python and the compiler level language, the C, or typically C or C++. Now, what Julia did, Julia learned from Java language. So Java has a concept called, Java is a compiler language. It has something called Java Virtual Machine, JVM. So when you write any code, it compiles in JVM, and that makes it very fast. So there is a compiler language, is called LLVM. So Julia, essentially native Julia language, uses this LLVM, low-level virtual machine basically, to compile the native Julia language. So that makes it way faster than R Python. And since it can process much faster, it can process much bigger data set typically than R Python. So they claim that it is much more suitable for big data processing and doing more advanced statistical computing. So that is their main claim. So Professor Kavita and I were working on, at least mainly Professor Kavita is studying this Zernike polynomial for a while now. Initially I was also involved, and we were, while studying this Zernike polynomial, we being you know, statistician, I always keep thinking of, okay, when I'm studying a mathematical model, how do I implement? It always comes in my mind. So I was doing search on what are the programming packages are available on Zernike Polynomial. And we found only uh, MATLAB and one MATLAB package, which is the most developed, and one recently developed Python packages are available on Zernike Polynomial. And turns out most of the data sets that are used need to be used for fitting a Zernike polynomial are going to be typically image data, and image data are typically very large, and um, it's big in nature in typically. So that immediately comes in my mind that, well, having a Julia package on Zernike polynomial will make it much more efficient. It will be much more efficient if we can have develop a Julia package. So it is, developing any package is always a bit of a ambitious challenge, but let us try. That is my goal, and I'm sure if we put enough effort, all of us put a little bit of effort put together, we'll make it a very decent and good package, at least to begin with, on a Zernike polynomial in Julia. So that is the starting point. Do you have any question? I mean, what we are trying to do here?
Yes, sir. I was wondering whether we'd have to know anything about, let's say, the physical uses of, like, the uses of Zernike polynomials in physics or image, like you said, image processing to, work on this, or will it just be at the level of, implementing certain formulas that have already been derived in some sense?
So when we will do at a programming stage, just knowing certain formula and implementation will be enough. But that is like, I feel like that way of looking at a problem is more like, you're doing a clerical job, right? Without understanding what is doing, you are being given a programming and you are just implementing it. Being a proper scientist, you would like to also know that, at least some of the applications of Zernike polynomial in depth. So I would recommend at least, I mean, Professor Kavita is working on Zernike polynomial, application of Zernike polynomial in, in ophthalmology. Okay, so at least you will know one of the applications in ophthalmology from Professor Kavita. There are other applications also, but at least knowing one good application while working, at least knowing will be, I think, would be good. So I think without but when we will develop the package, as you were saying, we only need to know that, okay, there is a matrix that needs to be inverted, or here is a formula that needs to be implemented in Julia. And when you are doing these operations, you just need to be careful that it is written in a somewhat efficient way. The algorithm you are trying to write, it is somewhat efficient way, that those things we need to be careful. So there it will be, you have to be wearing more hat of a computer scientist. But I think at least today we will start with the what is Zernike polynomial, what are the applications. So that part Professor Kavita will tell you. So I'm going to hand this thing over to Professor Kavita, and maybe next time when we will meet, that time we will focus more on how can we think of implementing it. Okay, so Kavita.
Yeah, I'm here.
Okay, so now it's to you. I have to just make you co-host, right? Yeah, so I'll make you co-host. Yeah. Okay. Now you're co-host.
Okay. Yeah, thanks. Okay, so welcome everyone. So I'm just going to give you an overview. I don't know much about Julia programming. Whatever work I've been doing is in MATLAB and Python. But I can tell you what this computation is about and what is expected from the toolbox, at least from this um ophthalmology standpoint. But the Zernike polynomials themselves are applicable in many other areas of optics. Okay. So I'll just give you a sort of background of what this is about, and then maybe we can talk about some details. So, uh, so Zernike polynomials are essentially a set of orthonormal bases for describing they're orthonormal on the unit disk, essentially. Okay, if you know some analysis and are
Or
comfortable with this language. Hello.
with, with respect to which inner product are the orthonormal?
So there is so I can there is this inner product defined with the integral. I think with the L1 norm.
Okay, integral f g dx, that integral -1 to 1 or -infinity.
-1 to 1.
Okay.
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 So with respect to that norm, this is a set of orthonormal polynomials on the unit disk. So the reason why they are used in the area that I'm going to talk about is the following. So this area is called as wavefront reconstruction. So wavefront reconstruction means the following, at least in the small area of ophthalmology, it means the following. So imagine that you have a sensor, okay, some kind of sensor. Okay, this could also be the human eye. Okay, the retina of the human eye. Okay, so this is some kind of sensor or retina. And you have light falling on this. Okay, so if there is nothing in between the light and the sensor, okay, then what you have is light coming as a plane. Okay, so that is called as a plane wavefront. Okay, so you can think of these rays being incident on a plane, and so the plane is what is propagating towards the sensor. Okay, so this is called as plane wavefront. And then there is nothing to do here. On the other hand, if there is something between, so you are viewing some object, and between that object and the sensor, there is uh, some something that makes these light rays deviate. Okay, it could be a lens. In most cases that I am looking at, it is a lens. Okay, so there's a lens between the light rays and the eye, and so now when the light falls on this lens, it's going to get deviated, right? So how to measure how so the idea of wavefront construction is to find an equation for this wavefront. Okay, so wavefront reconstruction means to find the equation that describes
Is that surface like arbitrary function, or is that a normal semicircular with partial?
no, so yeah, that's what we'll come to. Okay, we'll come to that in a moment. So this is the to find the equation that describes the wavefront. Okay, so this wavefront, although it means the front of the propagated waves, the equation that describes the wavefront will also describe this uh, whatever is the lens or whatever is the surface that is deviating these waves, light waves. Okay, so to find the equation that describes the wavefront, and since this is going to be in the surface, we are going to assume is a two-dimensional surface. Okay, so we can represent it with two variables w, x, y. Okay, so we want to find the equation that describes this wavefront. So at least in the case that I am studying it, this is going to be some lens. Okay, so you can think about it as a contact lens, for example. Okay, or you can think of it as the human eye lens. Okay, so this is the lens, and we want to study the equation of this lens. So now, why is that important? This is important for many reasons. So for example, you go to the doctor and you check your, suppose you are wearing glasses and you go to the doctor to check the power of your eye. Okay. So then if you have ever seen your prescription card carefully, there will be a spherical power, a cylindrical power, and an axis, right? So there will be these three things listed in the card. So these three things turns out describe parts of this wavefront, okay, parts of the lens of the human eye that are creating certain deviations in the path of the light. Okay, but there are many more. Okay, so there are finer things. So it turns out that this wxy, if you expand this as a Taylor polynomial, so Taylor polynomial in two variables, right? So this is going to be some, so, let me say f, for the moment, let me write 0, 0, but it could be some AB, okay? So f0, 0 plus f prime 0, 0 times, or we can do this around a and b. Okay, so whatever x minus, yeah, in general, if we do write it like this, x minus a, y minus b plus f double prime. So remember f double prime, f prime, f double prime. Now this is a function of two variables. So this is going to be like your first derivatives. This will be the matrix of second derivatives, and so on. Okay, x minus a, comma, y minus b. So I'm just writing it in a sloppy way, but remember your two variable Taylor polynomial. Okay, so the coefficients, there will be some coefficients that appear in the expansion. Okay, so if you don't do this with the Taylor polynomial expansion, but you do with some other, you can also do this expansion with respect to other bases, okay, other polynomials as BCs. So if when this expansion is done with respect to the Zernike polynomials, okay, then you get the Zernike expansion of wxy. Okay, so wxy can also be expanded using Zernike polynomials. So in short, I will just write this as summation aj sum zj xy. Okay, where zj is the jth Zernike polynomial. Then if these coefficients can be, so these polynomials are known. Okay, the list of polynomials is known, and it can be checked, they're orthonormal and everything. So if these coefficients can be found, okay, then you will have found this wavefront. Okay, so one thing is, if you know the wavefront already, then you can find its expansion. Okay, the other thing, way problem is, if you don't know the formula for the wavefront, then from certain other information, such as we will see, there are 2-3 different ways of using experimental information to derive or to find these coefficients. So if you find these coefficients, then you can use this expansion to say that the wavefront is approximated by this linear combination. Okay, so that is how it works. And the problem that I'm working right now on is the following, that so there are various ways of doing this. Okay, so estimating wxy from experimental information. So one is called modal reconstruction, something else is called zonal reconstruction. So here they are using Zernike polynomials. You could also use Fourier. expansion. Okay, Taylor expansion is also used. There is something called Seidel polynomial. So there are various ways. Okay, and various other expansions also. Okay, so the one that I'm working on is called modal wavefront reconstruction, and the idea in modal wavefront reconstruction is the following: that first of all, there is an experimental setup where you have the image sensor, okay, and something called a Hartmann array is placed in between the source of light and the sensor. Okay, so the Hartmann array is a grid with these holes at specified. Okay, it's a grid with holes on it. Okay, like this. So the grid size can change according to requirement. So usually this will be bigger. Okay. So this Hartmann grid is the Hartmann grid. And a beam of light is made incident on this. If there is nothing else between between these things, okay, between this and between this sensor and the grid, then when the light passes through the Hartmann grid, you will get a grid on your sensor. Okay, so these image points you will see on the sensor. And if it's a plane wavefront, then the expectation, of course, is that the if everything is fine, then there is the distances on the Hartmann grid are exactly what are reflected on the sensor. Okay, so you get a copy of the grid on the sensor. Okay, but so now if you want to test a lens or find the wavefront equation of a certain lens, okay, then what is done is that there is in the experimental setup, the lens is placed between the source of light. So here is your lens between the source of light and the grid. Okay, so now what will happen is this is going to cause so, or is maybe it is the other way. So I can show you a picture of the setup. So either the lens is here or the lens is here. I just need to check. So anyway, what happens is that, so let me suppose it's here. So then what happens is that this grid points are, instead of being in the original position as they are on the grid, they will appear a bit shifted because the light shifts because of the lens. Okay, the light beam has shifted because of the lens. Okay, so the grid points will appear in distorted positions. Okay, the distortion finally depends on how the light distortion is happening because of this lens. Okay, so now this aberration can be measured in the x and y. So this is a two-dimensional thing, right? The sensor. So you have the x and y direction on this. So with respect to these two directions, you can measure the deviations in the x direction and the deviation in the y direction at every grid point. Okay, and using these deviations, one can reconstruct the wavefront in the following way. So suppose wxy. So the mathematical idea is very simple. Suppose that you have an expansion of the wavefront in this way, okay, as a linear combination of Zernike polynomials. Then if you take the derivatives of w with respect to x and with respect to y, then what is going to happen is you're going to have this as summation aj, right? And then this is going to be summation aj dabba zj by dabba y. Okay, so now the point is that the coefficients remain the same. Okay, you can see that the aj's are going to be the same either way. Okay, and now these, on the other hand, can be shown to be equal to the deviation. So here the deviation in the x direction, suppose I call it delta x for a certain point. Okay, so for one point, so delta x at the, so let me properly give this a numbering. Okay, so suppose this is the Hartman grid. Let me take 4 by 4 for now. The numbering of there is a linear numbering for this. So you do 1, 2, 3, 4, go down, then 5, 6, 7, 8. That's the numbering for the grid points. Okay, and so on. Okay, up to 16. Okay, so this deviations are being measured at every grid point. So there is delta x at every xi comma yi, right? And there is a delta y at every xi comma yi, where I varies from 1 to 16. Okay, so at every point, if we evaluate this at the point xi yi, this actually equals delta x at xi yi divided by, so this can be shown, it's not difficult, divided by the distance d, where d is the distance between the grid and the sensor. Okay, and so that is why I think this lens is supposed to be on the left of the grid, but okay, that doesn't matter for us. So on the one hand, the derivative of w with respect to x is this, and on the other hand, it is this sum. Okay. Similarly, here this is equal to delta y. Yeah, let me write it properly. Delta y at xi yi is equal to derivative of w with respect to y at xi yi, which is equal to this sum again evaluated at xi yi. Okay, so we have that this sum at xi yi is equal to this measured quantity, and the derivative with respect to y this side is equal to this measured quantity. Okay, so when one is building the toolbox, the assumption is that you are given the either these images, okay, this kind of image with the shifts, okay, either that is given to you, or you are given the actual data which contains the locations of these points, okay, with the plane wavefront and with the wavefront that is being tested. Okay, this is called the lens or the wavefront that is being tested. Okay, so that will be the given data. Okay, and then you can compute this differences. So this delta x is simply going to be maybe your blue points minus the black points here. Okay, so those distances in the x direction and the y direction, because each point has two coordinates x, y, correct? So you can take the differences in the x coordinates and differences in the y coordinates. So that is going to give you a delta x and delta y. Now there are some finer things to be noted when it comes to building the toolbox. We can talk about it. That and yeah, this is something that maybe if you have used some OpenCV before, you already know, and if you haven't, this is not difficult to pick up. The point is that when the light falls through an array or anything, the light beam doesn't fall as a single point. Okay, it will usually be a region, some circular region. Okay, but when you need this for computations, you want to pick up a point. Now, what is done is one usually calculates the centroid of this region, okay, of this blur that is seen on the screen, and that centroid is taken to be the point xi yi for measurement. Okay, so sometimes from the data you might have to also calculate this centroid first and then proceed with the calculation. Okay, so there are various ways in which data may be presented, either as these blurs or these dots, or as readings of these points, okay, or simply as images, and from that images you have to do the entire processing. So okay, just to mention that. All right, so once we have this, so our main equations in this computation are that delta x over d is equal delta x over d at xi yi is summation aj zj sorry, derivative of zj with respect to x at xi yi. This is one equation, and the second equation is delta y over d at xi yi is summation aj dabba zj over dabba y at xi yi. Okay, so if anybody has any questions up to here, I can take them now, and then we can proceed after that.
Yes, ma'am.
So,
I actually have a
yeah.
question about like the domain that we're assuming over here. So we said that the Zernike polynomials are orthonormal over the unit circle,
Yeah.
but it looks like I don't really see where
The lens is the unit circle, or the human eye, the pupil of the human, the lens of the human eye, or the pupil is the unit circle.
Okay, so we
This-
are actually considering like even on the plane that we're viewing it at, that is the unit circle. Like we are.
Yeah. So this is actually 3-dimension. I mean, we cannot draw. I'm not able to draw, of course, but this lens is this circular lens.
Okay, so all these grid points are like just inside this like unit circular region, like where
Yeah.
or like we've scaled it down to like we've assumed.
So here you mean, right? Here, yeah,
Yes,
you
yes,
can
ma'am, yeah.
you can think of them as being inside a unit circle, or we will so if one is not considering this radius being 1, then normalize, but you will have to normalize and scale
Yes,
them
ma'am,
down.
yeah, that makes sense.
Okay.
Okay.
Or
Thank you.
otherwise this radius can come into play later in the calculation.
We have the
Okay,
rotational symmetry,
but
right?
yeah, that's the point. You will always have to normalize the data if it is not normalized already.
We will have the rotational symmetry, right? If you consider only one projection, it will just be circle of revolution, like a function of revolution, since this is circular, and the wavefronts are also.
So the problem occurs because this is not exactly this lens may not be smooth. It's not a smooth surface like this. Okay, there are aberrations along this surface that we want to measure.
Oh, okay.
Okay, so this wavefront, the whole wavefront measurement or reconstruction problem is that from this, can you say, so I will show you a picture of aberrations, how aberrations can be. Okay, and the aberrations can be very local in nature. Okay, at different point, there can be different aberrations. Or aberration means deviation from the normal way that it should look. The deviation from this smooth surface. Okay, this is a smooth surface, perfect surface. There is no, there are no ups and downs, no concavities, convexities on its surface. This is smooth. But in real life, or for the human eye also, there will be some aberrations. Okay, and yeah, and at every point, this aberration can be different. Although remember that we are still discretizing the data. So when this wavefront is a continuous function. Okay, but the whole process is done with using a discrete data. Okay, so there's only, I mean, you will still be sort of approximating this continuous function with some discrete data or a discrete information like these coefficients and all. Okay, so you will be locally, you will be able to say that at this point it looks like this, but you globally, it has the same limitations that any such approximation has. Okay. Yeah, any other question? Okay, so if there are no questions, then let's come down to just solving this. Okay, so how to solve this? Well, the solving problem is the solving is the easiest part because all we do is, so here suppose I have 16 grid points. Okay. Now, two things to note. One, the polynomials Zj, that is the Zernike polynomials, are known. Okay. And in fact, I will show you their definition in after this description is done. So Zernike polynomials, these are in fact defined using two indices, and the indexing can be changed from double indexing to linear indexing. There's a formula to go from one to the other. Okay, that's one thing. And the second thing is that Zernike polynomials originally are defined in polar coordinates. Okay, but of course, there you can convert them to Cartesian coordinates also. Okay, so there are formulae for all of these in polar coordinates, in Cartesian coordinates, and there are also known formulae like uh, uh, analytic formulae for their derivatives. Okay, so all z primes. So so there are for Zn rho theta as well as for Zn x1. Okay, so actually we don't require to go to Zn. We only require to go to the first derivative in all these reconstructions. So, and with respect to theta, okay, for all j's are known. Okay, that is not anything great. You just have the analytic, and you have analytic formula for the uh, polynomial, so you can derive analytic formula for the derivatives. Okay, so the list for these formulae are available. Okay, and so in order to solve this problem, we employ the generally the number of equations will be more than the number of variables here. Okay, so the number of variables, how many variables are there? So typically one goes up to 36. There are many, of course, right? So, but typically in practice, one needs to go up to 36 of these, 36 Zernike polynomials. Okay, so we want to estimate A1, and the numbering goes from A0. But anyway, for to make things simpler right now, I will just say we want to estimate A1, A2 up to A36. Okay, and we are given the left hand side, or we have experimental observations for the left hand side of this formula. So then we just form the system of equations which contains these quantities in the matrix. Okay, so these are known, right? We know the coordinates xi, yi for all i's. We know the analytic formula for these derivatives. So this quantity can be computed. Okay, so we can form the matrix with these computed quantities, and these come from experimental observation, and these AGs have to be estimated. So all this information can be put together in matrix form as follows. So you put daba z1 over daba x at x1 y1, okay, and so on. Daba z1 over daba x, or let's do it this way, daba z, since we want 36 of these, okay, 36 at x1 y1. Okay, then daba z2 by daba z1 by daba x at x2 y2. So all these evaluated at the second grid point, 36 over. In practice though, you will have to keep this 36 as a user defined input. Okay, the user may want to go beyond or below 36, and so on. Daba z1 by daba x, x36, sorry, x16, 16 grid points, y30, y16, daba z 36, daba x, x16, y16. Okay, so these, this actually forms half of the matrix. So you want to evaluate A1 up to A36, right, equals. So these are all. So look at if you multiply the first row of this with the column A. Okay, so I'm just going to call this column A. Then you get the first equation here. You will get the equation here, right? So with respect to the first coordinates x1, y1, or the first grid point. That's what this first evaluation. So it is going to be equal to daba x. I'll just pull out this 1 over d. Daba x at x1, y1. Okay. So this matrix multiplication gives rise to this first entry here. Then the second row multiplied by a is deviation at in the x direction at x2, y2, and so on. The last entry gives rise to deviation in the x direction at the grid point x16, y16. Okay, but you also have deviations in the y direction, so you can pile them up in this matrix. Okay, and so now we write down daba z1 by daba y x1, y1. So all the equations will come together. Z36 by daba y x1, y1. And just like we wrote the x derivatives, these are the y derivatives. X16, y16 to daba z36 over daba y x16, y16. Okay, so here you get on the left hand side your matrix. Okay, so this is your system of equations, and we can complete this also. Deviations in the y direction at x1, y1. Deviation in the y direction at x16, y16. So this completes the system of equations. These are all the equations that you know from this star. Okay, and now, so what are the dimensions of these? So 36. So suppose n is the number of coefficients that you want to estimate. Okay, so as I said, you will have to let the user define this. Okay, so you can say n is the number of coefficients to be estimated. Let k be the number of grid points in the Hartmann array. Okay, then the dimension of this matrix, as you can see, is going to be 2k cross n. Okay, and this one is n cross 1. Okay, and so this, as you can see, this is 2k cross 1. Okay, so you have 2k equations and n number of variables to be estimated. Okay, so this is usually over-determined set of equations because you will have, first of all, then you definitely need at least n grid points, correct? Whatever, so definitely you will have more than n grid points. You'll have many more, and it turns out that the more, for the least square solution of this problem, the more number of grid points you have, the better. Okay, so suppose I write the system of equations as some t a equal to d because deviations. Okay, so this is the matrix T, this is the vector A that we want to estimate. Okay, small a if you like, ta equal to d. Okay, so suppose this is the system of equations that we want to solve, then you can solve this using least square methods. And solving using least square methods is very standard. You can do this either using the pseudo inverse, or you can do this using SVD. Okay, any one of these things is possible, and that solves the problem. So once you have estimated this a, you're done. You have estimated those a's are called the Zernike coefficients. Okay, so you have estimated a, and then using that you can So it is used for many purposes. So let me stop sharing this screen and show you some images of aberrations and sort of how these Zernike coefficient determine what kind of aberration is seen on the lens. Okay, so in fact, you also, if you just Google Zernike coefficients and you look at the images, okay, you will see a lot of images. So I'm just going to share one of those images that are available on the Wikipedia page, okay, and describe it from there. Okay, so let me just share screen. Yeah. So you see this pyramid, right? So this pyramid, these are, so as they say here, these are the first 21 Zernike polynomials. The first one on the top here, okay, gives no information. This is the Z00. These are two indices, okay, Z00, or in linear indexing, this is Z0. This gives no information, okay. But now look here, this, what is this band telling you? This band is telling you that there is a tilt in the lens in some direction, okay. So this is the X tilt and this is Y tilt. So this information is given exactly by the coefficients Z1 and Z2, coefficient of Z1 and Z2, which means A1 and A2. Okay, the numbers that appear there will tell if there is a tilt in the lens. Okay, then the coefficients of Z3, Z4, and Z5 say if there are aberrations of this kind. So imagine this in a 3 dimension. Okay, so with the red and blue are being concave and convex. Okay, concavities and convexities in the lens. Okay, so actually we can also find images which sort of describe this in 3 dimensions. So yeah, here. So these are surface aberrations.
So there is a question, Kavita.
Yeah.
Ronil, what is the advantage of expanding it with respect to Zernike polynomials instead of some other polynomials? I think ortho.
Yes. Yes. Orthonormality is one thing, but there are also, yeah, there are a few analytic properties of the Zernike polynomials which make them more desirable. Okay, we can talk about them. I mean, if somebody is interested, we can go into the analysis of that later. So this is what I meant by tilt. Okay, the tilt in one direction, this sort of tilt, this and the numerical representation of this tilt is given by the corresponding Zernike coefficients. Okay, so this is what I meant by, uh, there is a defocus here. What it means is that, well, it's very difficult to explain, but it's an aberration in the lens. So here this is more clear when you go ahead. Okay, so it is more clear. So this kind of aberration appearing at a certain point. Okay, so the lens is distorted in these various ways. That is what these coefficients tell us. The measure of the distortion on the lens. Okay, uh, and so when I mean when you go to a doctor and they check your eye lens, how your lens is, they will get these numbers. Okay, so usually it is just astigmatism, defocus, and this astigmatism, two kinds of astigmatism that are being checked. Okay, for a normal human eye, this is enough. But if you go for some eye surgery or some corneal surgery or anything, then the ophthalmologist really have to look at a lot of these. Okay, because they have to determine very carefully exactly where the laser has to be focused, what changes have to be made to undo the aberration that is present in the lens. Okay, so in that case, in even up to Z36, they will look at, these are called higher order aberrations, and these are lower order aberrations. The lower order first 5, these are usually enough for your eyeglass prescription. or a contact lens prescription. These are enough. But if you need any other, or if there is any eye surgery or lens surgery being done, then the ophthalmologist have to look at even these. So this is only from the ophthalmology point of view, but also in telescope design, these kind of things have to be studied. So I don't know much about that area. I just know about this in the ophthalmology sense. Okay, so are there any questions? So the mathematical formulation is quite clear and not difficult at all. Okay. Yeah, if you have any questions, you can ask. So right now I have a MATLAB formulation of this, and we are working in MATLAB. There are a few MATLAB toolboxes available. There are also some people have tried Julia. So I was just searching and I found that some people have tried doing this in Julia. But so there are many variations of this experiment. So let me just share the main resource or the main reference that we are using for this paper. I can share the paper with whoever is interested. So this is sort of the experimental setup. Yeah, the lens is before the grid. This is the scanner. Okay. Here is the grid. Here is the lens. And from here, a beam of light is being projected on this. Okay. So this is the setup. And yeah, this is sort of a picture of that. I sort of lost thread of what I was going to say. Yeah. So yeah, sorry. Yeah, this is what I was going to say. So this Hartman grid setup is one way of doing this entire process. Okay. There is something called Shack-Hartman, which is a modification of this Hartman grid, in which instead of using one grid this way, they use small lenses called lenslets in place of every hole. Okay. That's called the Shark-Hartman grid. I don't know exactly what are the advantages of using Shark-Hartman over Hartman, but that is what people use more than the Hartman grid nowadays. And there are many other ways also of constructing the wavefront. Okay. So this problem is, I mean, if you want to build toolboxes for ophthalmologists like this, based on the Zernike polynomial reconstruction of wavefront, there is considerable thing to be done. You can also go ahead and do this with Fourier series or Fourier polynomials. Okay, there are, as I said, there are other bases also. So Zernike polynomials are not the only bases, although they have some very nice properties, which is why they are preferred. But it can be also done with other polynomials, and people do it. So there is something called zonal reconstruction also, which is done with Fourier polynomials. Okay. So that one is also quite popular. So you can also have a toolbox for that kind of thing. So the toolbox, if you ask me, what should it entail? It should entail, it should let the user provide a set of images from this sensor. Okay, that will be a sort of dream toolbox that the images from the sensor are provided, and the coefficient, the information, pertinent information such as what is the distance between the grid and the scanner. All this is provided, and then finally the coefficients have been estimated. That will be like a very useful toolbox. Yeah, I think I'm done with saying whatever there was.
Thanks, Kavita. Anybody have any question? So, Kavita, I was thinking, so a couple of things that was in my mind. So one problem that I'm facing is that I'm not sure. I know most of the students in this group are BSc program, and maybe couple of you are from MSc program, but mostly you are from BSc program, but with different years. So what I was thinking, I'll just create a Moodle page for this project, and you guys
Mm.
join that project. So it will be under the data science uh, heading, header in the Moodle page, and you guys please join that. Then we will have a reasonable idea. Okay, these are the people who are interested in this project and want to contribute in this project. Second thing, Kavita, I was thinking, if we can share that particular paper, uh,
Yeah.
which we want to start with, so that I will put it into the Moodle so that students.
Yes. So this paper I can share, and it has all the details of, I mean, whatever I said in short, the details are all here. Like this is the actual definition of the Zernike polynomial in polar coordinates, and this is the definition in XY coordinates, the Cartesian coordinates after conversion. Stuff like that. Everything is here, and I mean, for anybody who is interested in this, there's a good reference book, and that can also be shared.
Okay, okay, and okay. So Bijan Ray, he's saying, can we create a Discord server as well and work together in that? Um, I never worked on Discord server, so I'm not sure. So what is it? Can you tell me what is it exactly?
It's like WhatsApp only, but in a same server we have different channels. We can create like one for actual works, one for programming type, one for, and it also it has some bots that can support LaTeX in it, and also we can share codes on it that supports like unlike WhatsApp.
Acha. One thing we can do, it will be easier. So this project is mainly supported by Excadia Forum. So they're using something called Mattermost. It's an app basically, and this is exactly does what we are you just told me. I think what I will do, I will ask Ayush, who is basically uh, the point of contact for all these things. So I'll ask for first, you guys join uh, the Moodle page so that I will have a sense of idea that okay, who are the people who are really interested in, and I'll share their name and email ID with Ayush, and Ayush will send you the invitation to join this Mattermost. It's a kind of private app, uh, but it is very useful, and it just exactly does the same thing. So I think it will be very helpful. So, and in that way, my all other things are will be in the same page. And in any way, probably we are going to start a regular kind of uh, weekly seminar on Julia, so that you will get the invitation from Ayush as well on what are the things other people are doing on Julia. And so if you attend those Julia seminars, I think your learning on Julia will be much faster as well. Second, and the third thing I just want to tell you that what I realized when we started this project, that everybody has a different kind of system. Somebody is using Ubuntu, somebody is using Windows, somebody is using Mac. So easiest way to handle it is you um, you just install whatever version of Julia is compatible with your operating system, and then also have a Jupyter notebook and sync your Julia with the Jupyter notebook and write everything on the Jupyter notebook, and then just share your Jupyter notebook um, with your peers and me and everybody, so that anybody can look into your Jupyter notebook and know exactly what you are doing. So it will be much easier, and then contribute on that Jupyter notebook and send it back to you. So I think it will be easier if we just all agree to work on Jupyter notebook as the sort of a IDE, and so on the Julia. Okay. So all of you are with me, guys? So I think next thing I will do that I will upload this recording in the YouTube, and I'll set up a Moodle page in the data science under data science heading for this Julia project. Please join that project. And then once you join by this weekend, please join. Once you join, I will share your email ID with Ayush, and Ayush will send you invitation to join the Mattermost. Mattermost does exactly what Vijan is saying about Discord. So it's just a private app. I think it will be very helpful. Okay.
Sure, sir. Thank you.
Sure. Okay, thank you, Kavita. So I will also, I hope you will be helping, you will be at least meeting we can meet once a week. Is that okay with all?
So yeah, first we have to see who is interested in this, right? Or are you asking me about this or general Julia meeting you're saying?
I'm thinking I'll do a general Julia meeting more regularly, and whenever we have some problem with understanding Zernike polynomial or some detail, probably we will ask a separate meeting with you, so that
Yes.
that is fine, right?
Yeah, that is fine.
Okay, all right. Okay, thank you all then. Thank you very much. And I'll send you the invitations, and I'll set up the Moodle page. So see you soon then. Thank you, Kavita. Thank you very much.
Yeah, thanks everyone for listening. Yeah, bye.
Bye.